we are studying solid state. In solid state we have already studied the packing in the solids, and we also have studied the properties of these solids, and then we have studied how the defects are caused in the solids. In today's class we are going to study about two very important properties of solids, that is their electrical properties and their magnetic properties. Now coming to the first one, properties of solids. Electrical properties or electric properties. Solids conduct electricity in the range of 10 to the power of minus 20 ohm inverse meter inverse to 10 to the power of 7 ohm inverse meter inverse. In this range there are insulators, semiconductors and conductors. The solids range of conductivity in solids is from 10 to the power of minus 4 ohm inverse meter inverse to 10 to the power of 7. In the form of number line I am going to give this one. It will be easy for you to remember. Suppose this is the 10 to the power of minus 20 ohm inverse meter inverse and 10 to the power of 7 ohm inverse meter inverse. So conductors, it is up to 10 to the power of 4. This range is for conductors. And for insulators it is up to 10 to the power of 10. This range is for insulators. And from 10 to the power of minus 6 to 10 to the power of 4, it is for semiconductors. Solids conductivity ranges from 10 to the power of minus 20 to 10 to the power of 7 ohm inverse meter inverse. The conductor's conductivity is from 10 to the power of 7 to 10 to the power of 4 ohm inverse meter inverse. For insulators it is from 10 to the power of minus 20 to 10 to the power of minus 10 ohm inverse meter inverse. And for semiconductors it is from 10 to the power of minus 6 to 10 to the power of 4. So those substances which are there at the extreme, it will be, for example, if 10 to the power of 7 means it is shows high conductivity. In the case if it is 10 to the power of minus 20, it is least conductivity. Plastics and all these substances come here, and 10 to the power of 7 conductivity comes for metals. The flow of current in the solids is due to either ions or electrons. The flow of electricity in solid substances is due to ions or electrons. Now, if ions are the cause for the flow of the current, then that substance should be ionic compounds, and the flow or the movement of the ions will take place in the solution. Whereas electrons, the movement of electrons is seen in metals. The movement of electrons is seen in the metals. The flow of electricity is due to the movement of ions in ionic compounds and due to the movement of electrons in the metals. Conductivity in metals, conductivity of electricity in metals which are very good conductors is because of the number of unpaired electrons that are present in the metals. If the electrons are unpaired, at lower energy itself they can get excited to the conduction band from the valence band. Due to that, they are able to allow the current to flow through them. They offer least resistance. But if the distance between the valence band and the conduction band is more, then the flow of electricity will be less, which is seen in the case of insulators. Whereas in the case of semiconductors, the distance between the valence band and the conduction band is in between that of conductors and insulators. Now this difference in the energy gap is represented like this. In the case of metals, the valence band and conduction band are overlapping, or the distance between the valence band and the conduction band is very less in the case of metals. The distance between the valence band and the conduction band is very less in the case of metals. That is why the electrons are easily getting excited or they are easily moving in the case of metals. That is why they are allowing the flow of the current. In the case of insulators, the distance between the valence band and the conduction band is so high that the electrons cannot get excited from the valence band to the conduction band. This energy gap is very high, which is called as forbidden zone. This energy gap for insulators is very high, which is called as the forbidden zone, due to which the electrons cannot get excited to the conduction band. That is why insulators are bad conductors of electricity. Now coming to semiconductors, The energy gap between the valence band and the conduction band is in between that of the conductors and the insulators. So they can because energy gap is less, they can allow the electricity to pass through them. So that is why they are poor conductors of electricity. So in semiconductors, the energy gap is in between that of the insulators and the conductors. Germanium and silicon, they are good, they allow the current to pass through them, or they conduct electricity at high temperatures. So such type of semiconductors, germanium and silicon, they allow the current to pass through them at high temperatures. So these substances are called as intrinsic semiconductors. Germanium and silicon, they allow the electricity to pass through them at high temperatures. That is why they are called as intrinsic semiconductors. But the amount of current that they are able to pass is not so significant because it cannot be used for any practical purposes. That is, silicon and germanium cannot be used instead of other metals which are good conductors. So these substances are mixed with certain impurity, due to which the lattice of that substances will undergo a change and they will act as better conductors than without the impurity. So that process of adding the impurity to these substances like silicon and germanium is called as doping. So due to doping, the intrinsic semiconductors will be converted to extrinsic semiconductors. So this process is called as doping. Doping is adding the impurity to silicon and germanium. Now silicon and germanium, they belong to 14th group. So around each silicon there are 4 electrons, and these 4 electrons, when they are mixed with any other element which is having higher than silicon valence electrons or lower than silicon valence electrons, then there will be difference in the property of these the silicon or germanium, and then due to that it will be either allowing the current to flow through it because of excess electrons, which are called as negative or n-type semiconductors, or due to holes that are found, positive holes, which are what is the meaning of this I will tell you further, which are called as p-type semiconductors. Doping means adding the impurity to silicon or germanium to increase the conductivity of that substances. Okay, so here there are 2 types of semiconductors, in which depending upon what is the impurity that is added, it will be either p-type semiconductor or n-type semiconductor. Now here P means positive, because here what is happening is when the silicon is added with an element which is having less electrons than silicon. Now here if you see in silicon, silicon belongs to 14th group and the valency of silicon is 4. That is, the valence electrons are 4. There are 4 electrons on each silicon atom. So if you are adding a 13th group element, if you are adding a 13th group element like let us say aluminium. Now in aluminium, the valence electrons are only 3. So this aluminium getting added to this. So let us say this is, now it is not silicon. So in the place of silicon, aluminium is added. And aluminium, as its valence electrons are 3, so around aluminium there are only 3 electrons. So here the fourth electron is not there. That means it is not able to bond with the neighboring silicon atom. So here there is a hole that is created. There is no negative charge here. There is a vacant space. So that vacant space is called as the positive hole. It is called as positive hole because their electron is not there. So now what happens, there is a vacant hole here. So the electrons are able to shift from this place to other place. Due to that, what happens, the flow of current will take place. So in the p-type semiconductor, the 14th group element silicon, which is having 4 valence electrons, is doped with a 13th group element like aluminium. And due to the 13th group element, which is having only 3 valence electrons, all the 4 electrons of aluminium are not, 4 electrons are not there, so it is not able to bond with the neighboring silicon atom. So there is a vacant space. That vacant space is called as the positive hole. Now in the case of n-type semiconductor, here n is negative, which is due to the electrons. Now how this is happening is, when n-type semiconductor is doped with a 15th group element. Let us take for example arsenic. Arsenic belonging to 15th group elements, it is having 5 electrons. The valence electrons are 5. So because of the 5 valence electrons, when it is added to silicon, silicon has 4 electrons and arsenic has 5 electrons. So here what is happening? Let us say that here in this place arsenic has come. It is having 5 electrons. So first the 4 electrons will get bonded with the silicons which are there surrounding this, and 1 electron which has not bonded is free now. That free electron which is formed here, it is the cause of the flow of electrons. So this extra electron that is there here, which has not bonded with the neighboring silicon atom, is the reason for the flow of current in n-type semiconductors. In n-type semiconductors, n means negative, which is electron. The flow of current is due to the electrons. This intrinsic semiconductor is doped with the 15th group element in n-type semiconductors, and the 15th group element having 5 valence electrons is using only the 4 electrons for bonding, and the 5th electron is left free, which is the reason for the flow of current in this type of semiconductors. Semiconductors are having various applications. They are used in diodes, they are used in transistors, they are used in amplifying the sound also. These semiconductors are used. Semiconductors increase their conductivity on increasing the temperature, because on increasing the temperatures the electrons can be excited from valence band to conduction band easily. Not only that, this type of mixing of two elements of two different groups can also be used for making certain compounds which are called as 13 15 group elements, or 13-15 group elements. When they are combined, they are called as 13-15 group compounds and 12-16 group compounds. When 12 and 16th group elements are combined. Now these compounds are having lot of use in this solid materials, like for example 13th and 15th group elements, if you take aluminium, phosphorus, this compound, and then 12-16 group compound you can take zinc and sulfur. Okay, the compounds formed by the combination of 13th group element and 15th group element, they are called as 13-15 group compounds, and the compounds formed by 12th group and 16th group are called as 12-16 group compounds. Example, zinc sulfide. This type of compounds of the 13th-15th group and 12-16 group are prepared to increase the metallic or the insulating properties of the solids. They are also useful to make the substance hard by combining the elements of these groups. So to increase the hardness of the substance, to increase the metallic character, or to increase the insulating property, this type of combination compounds are prepared. Magnetic properties. Solids also show magnetic properties. Now this property of solids showing the magnetic property is due to the spin of the electron. Spin of electrons. The electrons spin in the clockwise and anti-clockwise direction. Due to this clockwise and anti-clockwise spin of the electrons, they show magnetic property. Now this magnetic property is due to the alignment of the electrons in the solids. So based on this, the alignment of the electrons, the substances are either magnetic or they are non-magnetic. That is, they get attracted towards the magnets or they get repelled from the magnets. Now this magnetic property of solids is measured in terms of which is given as magnetic moment, which is given as Bohr magneton, represented as nu b. The magnetic moment of the solids is given in terms of Bohr magneton, which is represented as nu b. So based upon the electrons, whether they are unpaired electrons or paired up electrons, or the arrangement of the electrons, the substances are classified into five types based on their attraction or repulsion towards the magnetic field, as into 5 types as paramagnetic substances, diamagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic. Based on the attraction or repulsion towards the magnet, they are classified into 5 types magnetic substances as paramagnetic substances, diamagnetic substances, ferromagnetic substances, antiferromagnetic substances, and ferrimagnetic substances. Now, paramagnetic substances means in these substances there are unpaired electrons. unpaired electrons. Due to this unpaired electrons, they get attracted towards two magnets. So due to these unpaired electrons, they get attracted towards the magnets. That is why they are called as paramagnetic substances. Example we can take O2, Fe. These substances are called as paramagnetic substances, and iron when its ionic state also comes under a paramagnetic substance which is having unpaired electrons. Now diamagnetic substances means all the electrons are paired up. All the electrons are paired. So due to this they are repelled by magnet. For example, water, NaCl. These substances have all the electrons paired up, that is why they are repelled by the magnetic field. Now coming to the third type, ferromagnetic substances. In these ferromagnetic substances, iron and iron-like metals, they are having the electrons they are arranged in such a way that all the electrons are in single direction. So this arrangement is called as the domains. The domains are arranged in single direction, like all the arrow marks, if you see here, they are pointing towards one direction only. They are arranged in one direction. These domains are arranged in one direction. That is why they are showing magnetic property. This is the reason why a magnet has north and south. Here we can take the example of iron and iron-like metals. Cobalt also can be taken. So in ferromagnetic substances, domains are arranged in single direction. The fourth type of magnetic substance is antiferromagnetic substance. Antiferromagnetic substances means these do not get attracted towards the magnetic field. They are repelled strongly by the magnetic field. Now in these antiferromagnetic substances, the domains are arranged in such a way that they get cancelled by each other. Due to this, what happens, they are not attracted by the magnetic field. If one is parallel, another is anti-parallel. The domains are parallel and anti-parallel, equal in number, parallel and anti-parallel. So they are repelled by the magnetic field. Like manganese oxide is an example of anti-ferromagnetic substance. Now coming to the last type of magnetic substance, ferrimagnetic substance. In these substances, the domains are arranged parallel and anti-parallel, but they are unequal in number. That means the number of parallel domains are unequal to the number of anti-parallel domains. That's the reason this is giving a magnetic property. It is attracted by the magnet. The example for ferrimagnetic substance is iron oxide, Fe3O4. So there are 5 types of magnetic substances based on the attraction or repulsion towards the magnetic field as paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic and ferrimagnetic. Today I have I have explained to you about electrical properties of solids and magnetic properties of solids, and each of these how they are classified also I have explained. I hope you understood today's concepts very nicely. Thank you very much.